Hi, this is the last part of our chapter of work on polar curves. It's exercise 9e. We're looking now at the area between two curves. Now, I think we saw a bit of this in exercise 9d, where you found the area of a curve, but now we're looking at, in particular, at the area between two curves. So let's have a look at this then. Start, alright, and fair. We've got 1 plus sine 2 theta for r, and it wants us to write it in the Cartesian form. So you should remember, for instance, r squared is x squared plus y squared, and that x equals r cos theta, and y equals r sine theta, and that effectively allows us to write sine and cos as x's and r's and stuff. So what have we got here? We've got x squared plus y squared to the m. Oh, this is what it wants me to get to. Okay, so let's start with the r equals 1 plus sine 2 theta. And there are a lovely formula for that. That's 1 plus, no, sine 2 theta is the same as 2 sine theta cos theta. I think I need to do that to get away from the sine 2 theta thing. And the great thing about sine theta, then I can write that as 1 plus y over r, x over r for the cos theta. So, oh, we missed out the 2. There's a 2 there as well. Okay, so that's equal to r. Now, I want to get rid of the r's. I suppose just a little bit of tidying up first. R equals 1 plus 2xy over r squared. Now, I'm going to move the r squared. So perhaps I'll move the 1 over first. So r minus 1 equals 2xy over r squared, and if I multiply through, I get r cubed minus r squared equals 2xy. I think I probably need some space, so I'll come up here. Alright, now this is, on the face of it, I would probably leave both r's there, apart from I've seen the answer. So I need to just have, I think, one of them. So I'm going to write r cubed equals r squared plus the 2xy, and this is, at this point, I'm going to get rid of the r squared is that. So on this side it's dead easy to do, x squared plus y squared, it says r squared, so I can just replace it plus 2xy. Oh, I see what they've got there now. And the r cubed on this side, well, that becomes the x squared plus y squared. Normally r is this thing square rooted, or to the power of a half. So that's to the power of a half, but I'm cubing it, so I reckon it's x squared plus y squared to the 3 over 2. And this is what I was thinking when I saw this. That looks to me, if I put that in the middle, it would have said x squared plus 2xy plus y squared. I think that's more normal to write it like that, because then you can write x plus y all squared. I actually think that's the answer. I think the m in the question is 3 over 2. And the n is simply 2. So I think I've proven it. Does it say? Yes, it does. Okay, good. Now here's our example then. We've got two curves have polar equations, and polar equations are those. This is a circle. You should recognize this as a circle, but this is one of those eggy type ones, I think. But anyway, it says find the polar coordinates of the point of intersection, and notice they use the 0 to 2 pi notation. So anyway, point of intersection, it's a bit like normal maths. They intersect when they are equal to each other. So I'm just going to do 3 plus cos theta equals 7 cos theta, and let's just solve that equation. So move that over. I think I get 3 equals 6 cos theta, and you subtract the cos. So therefore cos theta is a half, and inverse it gives us, I think, pi by 3, 60 degrees when you get half. Now, of course, you always normally do 360 minus that for cos. So here it's 2 pi minus that, which leaves 5 pi by 3. Now, we also need an r value to see where they cross. So I'll just do the pi by 3 initially. What's that? So I'll go in, you can use either equation theoretically. I'll use the C1 equation, and it says r equals 3 plus cos theta. Now, cos of theta at this point, that's nice. It's just equal to a half, so that's 3.5 or 7 over 2. Use the other one. It's at 5 pi. Oh, it's still equal to a half. So in both cases, I think it's 7 over 2. So I'm going to write this as, you always write r comma theta. So 7 over 2 comma pi by 3. And the second point of intersection is 7 over 2, comma 5 pi by 3. So I think that bit isn't too bad. It's the next bit I think that looks harder. Find the exact value of the area of the finite region enclosed between the two curves. Well, first of all, we'll need to draw it. So get your calculator out. This one is the eggy bit I was saying. It definitely goes further one side than the other. And this is the 3 plus cos theta. So that's r equals 3 plus cos theta. And I also want r equals 7 cos theta. Now that starts at the origin. I think it goes over to 7 as well. So it's a big old circle. It doesn't look much like a circle, but I don't suppose it really needs to. And that then is r equals 7 cos theta. Now I want to know the point at which these intersect. Well, I've already found that. And the reason I want to know those is I want the area between them. Now I think the area between these things, well, I actually think, now remember you're coming around in this direction. So going from 0 to 2 pi, imagine you start there. I'm just trying to justify this. So I suppose actually it's easy to think. We just want this area. I'd be getting all confused. Not confused, but trying to justify it. And really, the area between the two curves is the overlap, I suppose. So that's the easiest way to think. Now this is 0. And I'm thinking to myself, top and bottom are the same. So I'm only going to work out the top and then I'm going to double the answer. Now I'm thinking to myself, up to that point, this curve is what I'm after. I want the area which I'm going to colour in now, which is all of this. But you'll notice there was this little bit over here that I haven't yet done. So I think the area I want is the integral. Now you do this with the angle, so it's from 0 to there. That was on an angle of pi by 3. And the curve which we're playing around with there is the little one, the 3 plus cos theta. D theta. And then I've got this little slither of a bit, this bit here, goes in that little bit there. And I think that is the other curve, which is 7 cos theta curve, that matters now. And it's from that line, so starting from pi by 3, that slither. Now, because I know that that line goes straight up initially, that means it goes to pi by 2 d theta. And that's the area I've got to find. Well, it's not quite true, of course. What I've got to do is r squared it. So really, this should be all have squareds like that. And the other thing I suppose I've got to do is I'm meant to have a half in there. So I'm just apart from where, bear in mind, it's my final area will be just the top half, but then I need to double it to include the bottom half. So although it says a half, I then double it so it cancels out. So let's just multiply that out. So from 0 to pi by 3, it's 9 plus 6 cos theta plus cos squared. Alright, cos squared, of course, we should now know how to integrate. Plus this one is the integral from pi by 3 up to pi by 2. And that's 49 cos squared theta. Theta. Now, let's see if you remember how you integrate cos squared. And you should remember that there is a little formula we can use, which basically says cos squared theta. Now you can write it in different ways. I'm going to write it as it's a half cos 2 theta plus a half. So bearing that in mind, when I write it here, my area now becomes, well, it's the, shall I do this first bit first? Yeah, I'll call it area 1. And the area 1 is the integral from 0 to pi by 3 of 9 plus 6 cos theta. It says plus cos squared, so plus a half cos 2 theta plus a half, so that's 9.5. So that's like 19 over 2 d theta. So I'm going to integrate that. and I get 19 theta over 2 plus, now remember, sine, cos, minus cos. I am integrating, so I go upwards. Cos simply becomes a sine. So this simply becomes 6 sine theta. And half cos 2 theta. Cos becomes a sine again. The 2 gets, effectively goes on the bottom, doesn't it? So I get a quarter of sine 2 theta. Now this is in between 0 and pi by 3. So if I put those in, put pi by 3 and I get 19 pi over 6. Pi by 3 is 60 degrees, sine of 60 is root 3 over 2, so that's 6 root 3 over 2 plus 3 root 3. And my last bit says a quarter sine 2 theta. Now that's really like sine of 120, which I think is root 3 over 2 again, so I think that's plus root 3 over 8. Root 3 over 8. So I'm going to just leave that to one side. I've now got to do the second one. I'm going to do it on the next page. Oh, I've got some answers there. So this is now the integral from pi by 3 to pi by 2 of 49 cos squared theta. And I've already said you can replace that with a 49 lots of a half of cos 2 theta plus a half, so that's 49 halves between those two values, pi by 3 and pi by 2. So if I, oh by the way, one thing I didn't mention was if I put 0 into this, that becomes 0, that becomes 0, that becomes 0, and therefore I didn't need to worry about anything to take away. Whereas here I might need, I might need it a bit more here. So on this one, when I, that's still to be integrated by the way, I've written that slightly wrong. Now when I integrate that I get 49 over 4. Cos becomes sine, we just agreed that, sine 2 theta plus 49 over 2 theta. So if I substitute those two numbers in properly now my notation is starting to look better. I get, well again it's sine of, well that's sine of 90, but I double it to a 180 and that I know is 0. So that's 0 plus 49 pi over 4. If I put pi by 3 into that, I've already said that gives me root 3 over 2. So it's 49 root 3 over 8. What am I doing now? I'm putting that. Yes, that's right. I'm just realised I've made a mistake. So I put the first two in with that, and now I'm switching to this. Yes, plus 49 over 6 pi. Good. So it's a bit of a mess, isn't it? So if I just calculate that. So what have I got? I've got here 49 pi by 12. I just did it on my calculator. So to save me making daft mistakes like I normally do. And if I take, so that's dealt with that, and I've also got this minus 49 root 3 over 8. Now don't forget this is area 2 really, and there was area 2 equals this, and there was additionally area 1, and I wrote down area 1 as being, how to put it here, it was 19 pi by 6 plus 3 root 3 plus root 3 over 8. I probably could have done something with that already, but when I typed them in, I added this one to this one, I then get a total area. And I think it's the same as I've got down there. In fact it is. It's 29 pi by 4 minus 3 root 3. Just check on the calculator. So it's not very nice, but interestingly the area between the two curves was literally what it said. We found the area, so the overlap between the two curves. So that's what we ended up getting. Notice it did say halves, but because we wanted both parts of it, I ignored the halves and that gave me 2 times it. So anyway, that was that question done. And then in lesson then we'll have a look at exercise 9e. Which will be more of the same, I suspect, but there might be a few surprises as well. So, thank you very much.